So we're going to be going over the stats final for semester one. This might take a while to do because there's quite a few problems to go over, but let's get started. So the first problem here simply says convert 15 over 40 into a decimal and a percent. So what you do here is you want to first go to the decimal just by dividing. So all you do is you take 15, whoops, let's turn it on first. Take 15 divided by 40, and we end up getting 0.375. So I'll write that here, 0.375. So that's our decimal, and then to convert that into a percent, we're going to take 0.375 times 100, because again, percents are out of 100, or simply just move the decimal spot over twice, it's the same thing, and we get 37.5%. So this is just a matter of dividing to get to here, and then timesing by 100 to get to your percent. It's two-step operations. Number two says find the variance for the given data, round to the nearest tenth. So we could try to find the variance of all this by hand, which would take a while, or we could use our calculator. So the way you do this in your calculator, let's clear the screen there, is you go to Stat, you go to Edit, you enter the numbers into your list. So we'll do 1, 5, -6, 3, and 8. So we got that list all set and ready. And just double check to make sure. 1, 5, -6, 3, 8. Okay, we're all good. Then you're going to go to Stat again. You can go over to Calculate, 1 var stats. You're going to click Enter, Enter again, and it's going to pop up a big list of numbers here, none of which is the variance. However, the way you can get your variance is you take your standard deviation and you square it. So this little s of x here, 5.263, so we'll write that down here, 5.263. That's our standard deviation, and the variance is simply the standard deviation squared. So we can write, let's close this out here. We can write 5.263 squared, and we get 27.699, which if it says to the nearest tenth, would be 27.7. So that's equal to 27.7. Now again, getting this by hand is kind of difficult because you'd first get all the squares, then multiply, and then subtract. There's a big long process that we've gone through before by hand, but to save yourself some time on the final, a lot of time on the final, again, all you do is you go to Stat, make your list, go to Calculate, Calculate, click Enter, find your standard deviation, the little SX there, and then square that number to get your variance. So it's just the square of the number here. This will not tell you what the variance is, but it'll give you the option to get it kind of quickly. All right, let's go on to number 3 here, and 4. A group of plants was cultivated using chemically treated water. Is that an experiment or an observational? Well, if it's chemically treated and we're testing to see how well it works, that'd be an experiment. Experiment. Because we are altering, whoops, there we go. Let's try that again. Boop, there we go. So we're altering the study there. We're altering the plants. So I lost my train of thought there. And that's going to result in an experiment because we're chemically treating the water first. Population of deer over the course of 10 years. Again, assuming we're not altering the population by, hunting them or giving them food to make them grow faster. Assuming we're just letting them be, this would be an observational study. So this is observe. So we don't, again, although during an AOA, we don't hunt them, we don't introduce any predators or any vegetation that would make them grow faster. We just let them be. We're looking to see what happens. So that's an observation. So if you do something to the things, that's experiment. If you just let them be, that's observation. So find the mean for this data of the given sample. Okay, well, once again, we can do this by hand or we can use our calculator. You can do this one of two ways. You can actually just add all these together in your calculator and then divide by 1, 2, 3, 4, 5, 6, 7, 8, 9. Or, once again, we can make a list. So we go to Stat, Edit. Let's clear this list. So we go Up, Clear, Enter. That'll clear the list. Let's type in our numbers, being very careful here. 37.5.51. Enter. 370. 0.13, 339.04, 466.92. I'm making sure I don't make a mistake here because I don't want to go back and re-enter all these. 180.97, 165.25, 421.73. Looks like I have quite a big jump here, so my mean probably isn't going to be too accurate a representation because I have quite a large spread, especially with those 100s down below there. That's going to throw off my mean a little bit, but that's fine. So we entered all our numbers. We go back to stat. We go over to calc. We click enter. We click enter. And this little X bar on top, that is our mean. So 365.91, 365.91 is our average value. So this value right here. So again, we don't necessarily use all these yet. We're mainly focusing on the X bar for our average. Again, 2 decimal spots is how you round. So after the 1 is a 2. So you keep the 1 a 1 and just leave it as 365.91. Again, calculator will help speed a lot of that up. Number 6, find the original data from the stem and leaf plot. So basically we're going backwards. They give us the plot. We want to figure out what data set are they taking it from. So in this case, it's best to just do one at a time. So this one here, 38, and then it has these leaves. So we're looking for a 38 with a 47, and then a 38 with a 91. Because all you do for a stem and leaf plot is you take this number, take these numbers, and put them together. So this number, put them together. That's the original number that was in the plot. So let's see where we find those. Right here, 3847, 3891. Now let's check to make sure they're not in anywhere else. This is a 3847, but no 3891, so that can't be it. This doesn't have either, and this doesn't have either. So it has to be B. So sometimes you get lucky, and all you need to do is check one row, and that's the only row that shows up. So you'll circle B here. If 2 rows had 3847 and 3891, if this was in both, then we'd have to go and check 39, make sure that was in there, and then check 40, make sure that was in there. But that's why you just want to check one at a time, because usually you can eliminate quite a few with your first go. So check one row, make sure it's listed. If it is, great, use that one. For number 7, find the mean of a probability distribution. So they give us a probability distribution right here. And the way you find the mean of a probability distribution is you multiply, then add. You actually do not divide when you're trying to find the mean of a probability distribution, because remember, probabilities are already divided themselves. These are already something divided by the total number. So what we're going to do here is we're going to multiply our x's to our probabilities and get our sets of values there. Draw my arrows. So 0 times this is just 0, that's a freebie. 1 times that is just that, again, another freebie there, because 1 times anything is just itself, even if it's a weird decimal. 2 times 0.3456, so if we do that, we get 0.6912. And then we have 0. So 3 times that, actually it wouldn't be 0 point. If I do that correctly here, let's see, that would be 1.0368. And then 4 times this, let's check that real quick actually. So 4 times 0.1296 will give us 0.5184. So 0.5184. So x's times probabilities, we get this here, and then we're going to take all these numbers and we're going to add them together. And if we add all those up, we end up getting 2.4. Which is good, because that's somewhere in the middle of my list of possible answers here. Remember, x is the number of possible results I can get. So this is the probability for the number of adults who have a college degree if you select 4. So if you pick 4 people from this population, what's the probability that 0 of them have a college degree? What's the probability that 1 of them have a college degree? So if we find the average, we say on average, if you pick a randomly selected adult, 2.4 of them are going to have a college degree based on the probability, which again, obviously we can't have 0.4 of a person, but that's okay because we're talking about an average here. And that makes sense because 2.4 is kind of in the middle of our two biggest probability sections, which are 2 and 3. So 2 and 3 have the highest likely chance of happening. So the average should be somewhere around that area. And 2.4 is pretty close to the middle of that area. So it's a good indication that we probably got it right. So again, multiply, then add, then done for the mean of a probability distribution. Remember, we have a few different kinds of means here depending on what we're doing. So this is the probability mean, very quick and fast to do. Make sure we get it right. So this one wants us to construct a relative frequency distribution. Again, when you hear the word relative, think percents. This is a percent frequency distribution. So you have to change all these frequencies into percentages. So the way we do that is we do some division. So let's draw some arrows here. First, we have to figure out how many people were in our little survey here. So we do 4 plus 6 plus 8 plus 2. So we add all these together to get our total number of surveyed. So this ends up being 20. So that's the total number of people that were surveyed. So how do we get the percent? Well, we take the number of people in the category, which in this case for 4 to 6 is 8. So we put a little 8 here, divided by the total. This is going to be 4 divided by the total. 6 divided by total. And 2 divided by total. So we're just changing them all into percentages. This would be 0.4 or 40%, 0.2, 0.3, and 0.1. If you want to change these to 40, 20, 30, and 10, that's also okay. You can certainly do that. If you want to keep them as decimals, that's fine too. But either way, we're going to need to make our table here. I'm going to try to do this the best I can here. So we have 4 to 6 range, which was 0.4. So we put a 0.4 there. 40% of them were in that range. 7 to 9 range was 0.2. 10 to 12 was 0.3. And 13 to 15 was 0.1. So all we did was take these percentages and slap them next to the appropriate categories. And that makes our relative frequency table here. So this would be my age. Again, I'm a little bit messy here because I'm trying to write with a mouse, so I apologize. This is my age, and this is my percents. Just to make sure I label my columns there. So again, relative frequency, change your values into percentages, put them in a table, and then you're all good. So number 9, find the mode. Again, the mode or modes are just the numbers that occur most often. So let's count how many times a number occurs. So we have 12, which occurs twice. 14 occurs twice. 5 occurs once, so that's obviously not going to be part of the mode. 13 occurs once, so that's not going to be part. 16 and 8 both occur once, so that's not going to be a part of it. So the two numbers that occur most often are 12 and 14 because they occur twice. So my modes are going to be 12 and 14. Remember, you can have more than one mode. That's fine. You can't have more than one mean, and you can't have more than one median, but you can have more than one mode. So number 10 is another type of average problem. So it says gets quiz grades of 65, 75, 83, and then 86 on our final. It says the quizzes are worth 15% each, and the final is 55%. What is her final grade, or what is her weighted mean? Well, to find the weighted mean, what you do is you take all your values, you multiply them by the percent of the weight, or just the weight in general. So this would be multiplied by that, and then you add them together. So let me show you what that means here. 65 on her first quiz. Well, how much was her first quiz worth of her grade? Well, it was weighted at a 0.15 or 15%. So right there. So 65 grade on her first quiz, 15% total worth. Her second quiz was also worth 15% of her grades. That's also going to be 0.15. And her third quiz was also worth 15% of her grade. So it's also 0.15. And then her final which she got an 86 on, was worth 55%. So 0.55 of her grade. So we have first grade 15%, second grade 15%, third grade 15%, and final grade 0.55%, or sorry, 55%. Now, normally what we would do is we take and divide by the total number of weights, but if we divide by the total number of weights, 15 or 0.15, 0.15, 0.15, and 0.55, all of these add together make 1. So I'd just be dividing by 1 anyway. What usually happens with percent weights is that they add up to 100%, so you'd end up dividing by 1 and nothing would change. So from here, you can just add all this stuff together here after you multiply. So times there, times there, times there, times there, and then add together, and you end up getting 80.75% as her final grade. So once again, a weighted mean is simply take your numbers and multiply it by the respective weight first, in this case 15% or 55%, and then add them together after you're done multiplying them. The last step again would be to divide by the value of the weights added together. But if I add all my weights together, 0.15, 0.15, 0.15, and 0.55, it's going to add up to 1, so I don't need to bother with it with percent weights. Just a little bit of a step I can skip. So 11, probabilities here. So 350 horses show up to a bar, 120 of them have long faces. Find the probability that the next horse to show up will have a long face. So the probability is simply the number of results divided by the number of total things. So how many horses showed up with long faces? Well, 120 of them. So number of, we'll say successes instead of results. That might be an easier way to describe it. So number of successes, 120. Number of attempts, 350. So we have 120 horses, 350 which have long faces. So number we want, long faces, divided by the total, 350. And we divide this and we get 0.34287, which just ends up being 34.29% if you're rounding to the nearest tenth. Or you can just write 0.2857. But again, to get here, all I did was times 100 to get into percent form, which is fine. Or if you want to leave it as a decimal, that's fine too. But the main idea here is, again, the number of things you want, which in this case is horses with long faces, divided by the number of things total, which in this case was 350. So number you want divided by total, that's how you get basic probability with this problem here. There's more advanced probability that we get to later, but for right now, this is the basics. Number of things you want divided by number of things that happened in general. A stance final is worth 40 points. If a student earns 35%, how many points do they earn? Well, this is just a percent problem. So you have 40 points possible. A student earns 35% of them. Well, 35% as a decimal is 0.35, so let's make sure we write that down, 0.35. So I'm going to take this times 0.35. So it's what they could have gotten, 40 points, what they could have gotten, times the decimal form of the percent they did earn, which is 0.35. We multiply this together, and we get 14. So they got 14 points. If you want to check your work, you can do 14 over 40, and that will get you back to 35%. So again, it's the percent as a decimal times the total amount, and you get your amount of points that they got. And 13 is another probability problem. It says if we pick a person at random from this list here, what's the chance that we select an occasional smoker given that they are a woman? So if it's given, that means we're only selecting from women. We look at our study and pick out all the women, and then we try to pick out an occasional smoker from them. So we first have to figure out how many women in total were surveyed. So if we look at the women column, it looks like 503. So 503 total women were surveyed. So that's going to be my bottom number, 503. So this is part of my given. So this is what I was given. So given that they're a woman, or a woman, I should say. So that's on the bottom there. And then the number I put on top is of those 503, how many are occasional smokers? Well, if we look through the women column here, 44. We're not going to use 33 and we're not going to use 77 because those include the men's numbers. I just want the women number because I'm looking for, given the fact that they're a woman. So I put a little 44 on top here, and then do my division, which if you change it to a percent, comes out to be actually, if you change it to a percent, it'd be just 8.75%. So if you want to do the division, it'd be 44 divided by 503, and then you take that and times it by 100 to get your percent, which again, we round that 4 up because behind it is a 7. So when you're given a portion, when it says given something, that means you're restricting your view to only that something, in this case, only women. So that's why we ignore the men column and we ignore the total column, because it says given that they're a woman. So we're only looking for the women results there. So number 13 again, because evidently I mislabeled them. So number 13 says, at the Criminologist Institution or Association, we have the following results about the most important cause of criminal behavior, and we want to find which of these charts here fits that result. And the first thing you want to be careful of is the fact that all of these charts down here, all these multiple choices, are relative frequencies. So all these charts display percentages, not actual values. So a lot of people make the mistake of looking at this and they say, okay, poverty is 53.9. So they're going to look for which bar has poverty closest to the 50 mark. And then they'd say, okay, well, it's probably this one because 53.9 is above 50. This bar is above 50. So I have to circle that. But that's not what you want to do because this is a frequency, not a relative frequency. So you want to look at these in terms of percentages. Well, how do you do that? Well, just like we did before, we're going to add all these together first. So if we add them together, we end up getting 154. And then we're going to pick one, change it to a percentage, and figure out which chart has it best. So for example, poverty would be my largest one. I'm going to say 53.9 over 54, or 154 rather. Make sure I type that in right. And we get 0.35. So 35% of the people chose poverty as the most important cause for criminal behavior. So I'm going to look for which chart has poverty closest to the 35% mark, which would be one of these two. This one has poverty over here. It's around the 20 mark, so that can't happen. And this has poverty above the 50 mark, almost close to 100%, so that can't happen. So it has to be one of these two here, because both of those have poverty around the 35% mark. And the reason I'm going to know that it's this one here is because this one doesn't include the other. This one has the other portion right here. This one doesn't, so that can't happen. So it has to be chart B, because poverty is at the closest mark there, and it includes the other, whereas this one does not. Now, another thing you have to know about Pareto charts is they have to go from largest to smallest. So this one obviously wouldn't be it because it starts at the smallest and it kind of goes bouncing around there. Pareto charts always have to go big to small in that order. They can't be bouncing around. So that's, I can eliminate D right away just from that. But again, read your problems carefully. Make sure to see whether the chart is asking for relative or normal frequency. And if it's asking for relative frequency, change these two percents first before you go looking for them. And again, to change it to percents, you have to figure out how many frequency you have total. So you add them all together to get your total frequency. And then you took the portion that you were checking divided by the total frequency to get your percent for that portion. And then you're going to check to see which graph matches that up. So 14 says we want the z-score for Bob. So it says the average text speed is 40 words per minute. So that's our x bar or our mu or whatever. Standard deviation is 6. That's another piece of important information. Again, if you have trouble with word problems, make sure you have a highlighter or something with you to highlight or underline or something the important numbers and the word that goes with them. For stats, it's very important to know what those numbers mean too, because that's going to change their place in the formula. So 40 words per minute, that's our average. So I'll link all the way over here to average. Standard deviation is 6. This is Bob's rate is 48 words per minute. That's his rate. And then we want his z-score and whether it's going to be usual or unusual. So if you don't remember the z-score formula, it goes as follows. The z-score formula is the value minus the average divided by the deviation. So it's what the person can do minus what the average is in general divided by the deviation of the entire thing. So Bob's value is 48.4. By the way, sometimes this is listed as X bar, depending whether you're doing sample or population, which is fine. X bar and mu in this case mean the same thing, so you don't need to worry too much about them. So Bob can text at a rate of 48.4 words per minute. So that's his X, 48.4. The average person, it says up top here, is 40 words per minute. So we'll put a little 40 there for the average person. And the deviation is 6, so we put a little 6 down there. And we plug this and go. So 48.4 minus 40 is 8.4. 8.4 divided by 6 gives me 1.4. So that's his z-score. Again, this is how many deviation he is away from the average. So he's 1.4 deviations above the average, or 1.46s, because that's a deviation, above the average person. So he texts a little bit faster than the average person, but is it unusual? Well, to be unusual, you have to be more than 2 deviations above. So his score right here is not unusual because his score is within 2 deviations. So his score would be considered quote unquote normal because it doesn't hit the 2 deviation mark. So he texts faster than average, but not unusually faster. He is not an anomaly, I guess you could say. So again, z-score is a very short formula. You have to remember that the value of the person comes first before the average. Number 15 says using this pie chart, find the answer to the problem. So first thing to note is that we have a total of 989 vehicles. So we have to know those total here. And it says of that, 30% are hatchbacks, 28% are pickups, and so on and so forth. It says find the number of convertibles. Well, this is just a percent problem dressed up a little bit. So to find the number of convertibles, you're going to take how many vehicles total? 9189. And times it by the percent of convertibles, which in this case is 0.15. It's just, again, another percent problem. Total number of vehicles times the percent that you want, which in this case comes out to be 137.8.35, which we can't have 0.35 of a car, so it ends up being 137.8. So once again, this is just a percent problem with a circle graph. Don't freak out about the graph. It doesn't make this any problem. It doesn't make this problem any more involved or anything like that. It's just total number times the percent of the category you want, and that's going to get you the value that you're going to circle. So this is actually asking for a cumulative frequency distribution. So it's another type of distribution rather than relative frequency. And what a cumulative frequency is simply adding up the numbers as you go. So let me show you that here. So we're going to make another chart here. We'll have income. And we'll have frequency. I'll just put F here for frequency. We're still going to have the same category to start with, 200 to 300. And that's going to start with 69. Now, each category is basically going to consume the other. So this is 200 to 300. The next one would be 200 to 400 because it's going to take everything in this category and everything in this category together. That's what cumulative means. You're accumulating stuff as you go along. So everything in this category synced up with everything in that category, which means I'm going to do 69, my previous number, plus 73, which is the next number. So these two numbers add together, which give me a total of 142. Then my next one's going to be 200 to 500. Because again, I'm consuming all three categories together. So I'm going to take my previous value, 142, and add it to my newcomers, which is 81. And that's going to give me 223. And then my last category is everything. So 200 all the way up to 600, which means I'm going to add everything together. Or if you want to do it simpler, 223, which is what I have so far, plus my last amount, which is 65. And that's going to give me 200 88. So these, if I try to outline that here, there we go. These would be my cumulative frequencies: 69, 142, 223, 288. As you notice, if you're doing a cumulative frequency, your numbers should always be getting bigger. You should never have numbers get smaller and then bigger again, or just get smaller. They should always be getting bigger because you're accumulating everything from the previous categories in addition to your new value. Sometimes it might stay the same if the category is a 0, but other than that, it should always be getting bigger for a cumulative frequency. So we're identifying whether it's random, stratified, systematic, clustered, or convenience. So random, by the way, just in case we don't know, random is simply kind of the default answer. If it's none of these other ones, then it has to be random, just because it's picking it at random, assumingly. So a tax auditor selects every 1,000th tax income return that is received, assuming for an audit, I guess. So hopefully you're not the 1,000th person. And we want to figure out, is that which one of these is that? Well, if you're taking every 1,000th, that means you have a system. You're taking every 1,000th. That's your rule, your algorithm. So that'd be systematic. Because you have a system, you have a rule in place. 1,000th, every 1,000th is going to be the ones that you pick. So if you have a rule in place, that's like every X number, that's systematic. 18 says 30 students are selected from each grade level at a high school. So this one, you're splitting them up by grade level. It says each grade level. So you're splitting them up into freshman, sophomore, junior, and senior. Whoops, senior. So you split them up into grade levels, which automatically makes it either clustered or stratified. So it's not going to be any of these here. If you're splitting the groups, it's going to have to be one of these two. And the difference is that cluster is when you take all the people from a few groups. So I would take juniors and sophomores, and I would take everybody in those categories. Or I take sophomores and seniors and take everybody in those categories. So you pick the groups and you take everybody in those groups. Stratified is when you take a few people from all groups. So this is only a few groups. So a few groups. This deals with all groups. So in this case, my answer would be stratified, not clustered, because I'm taking it from each grade level. So I'm taking a little bit from all groups, 30, 30, 30, and 30. So if I'm sampling a little bit of everything, it's stratified. If I just pick two groups and go with them, that'd be clustered. So 19 here. It says we have 78 high school students, 24 are zombies. If 4 are selected at random, what is the probability that all 4 are zombies? Assume no replacement, which is important in this problem. So the way we do this is we set up our 4 stations here. So we have first senior, second senior, third senior, fourth senior. So we're going to pick 4 of them. And if we pick the first senior, what's the chance that they're a zombie? Well, we have 24 zombies and 78 possible seniors to pick from. So the first person has a 24 out of 78 chance of being a zombie that we pick. Now, if I pick this person, they're a zombie, that means there's only 23 zombies left for the second person to be, and there's only 77 people total now because I picked one over here. So the second person has a 23 out of 77 chance. The third one, well, now there's only 22 zombies left because I picked 2 of them before, so 22 zombies left because 2 of them are over here. And there's only 76 people left to choose from because, again, I'm going with no replacement, so I can't pick the same person twice. And lastly, now there are 21 zombies left and only 75 people to choose from because, like I said, I've picked 3 zombies already and I've picked 3 people already, so my numbers are going down. And then I'm going to multiply all these together because probability almost always deals with multiplication. And in this case, you're going to end up with 0.007449, which as a percent is 0.7449%, which is a pretty low chance for all 4 to be zombies, which hopefully is a good thing. So If it's no replacement, remember your numbers are going to change each step. If this was with replacement, then it'd just be 24 over 78 all 4 times. So with replacement, it's pretty easy because it's just the same fraction 4 times or 5 times or 6 times or whatever it is. But without replacement means you have to kind of keep track of how your numbers are changing from each category. Number 20 says Little Red Riding Hood must deliver baskets to 5 grandmas in the forest. If she can do this in any order, how many routes can she take? Well, once again, let's make 5 sections here. So first possibility, second possibility, third, fourth, fifth. So she has 5 houses to go to. And her first route, she can go to any house that she wants. So there's one of 5 houses she can go to. So 5 possible houses she can run to for her first one. What about for her second one? Well, if she goes to this house, that means there's only 4 houses left for this one. So she's gone to both of these houses. So what's the next house she has to go to? Well, it's one of 3. Well, she's gone to 3 houses now. So how many houses does she have left? Well, she has 2 possible choices for her next house. And the last one is just 1 possible choice for her last house. So she has 5 choices for which one she goes to first, 4 for which she goes second, then third, then 3, then 2, then 1. And once again, we're going to multiply all these numbers together. And we're going to end up getting 120 possible routes that she could take. Because again, she can do this in any order she wants. By the way, this is also a permutation problem of that NPR stuff we did, but it's probably easier just to write it like this because then you don't have to bother with where the N goes, where the R goes, and what's the N and what's the R and all that stuff there. Just think about it in terms of sections. First possibility, second possibility, third, fourth, fifth, and then how many possibilities are in each spot. Notice that this is not a probability question though, so I don't do any fractions. This was what's the probability, so each one was a fraction. This was simply how many routes, so each one's a nice whole number. So just be aware of that. If it doesn't ask for probability, you don't need to use a fraction. Number 21 says a binomial distribution has the following values. Find the probability of x successes. So it gives us our stuff here. So x successes in a binomial distribution. This is something we're going to do in a calculator. If I want x successes, that means I'm looking for a certain number of successes, in this case 6. So I want to know what's the chance that this works, whatever I'm tracking here, what's the chance that it works 6 times? So if I want an exact value, that is going to be a PDF function. So we're going to go to our calculator again, clear it out. We're going to go to second vars, which on top there says distribution. We're going to go down to where it says binomial, and we want the PDF one because we want an exact number of successes. If this was at most, at least, or more than, or less than, then we'd use the CDF part, but we want exactly 6 successes, so we're going to use the PDF. So we click that, and then type in what we want. So we have 20 trials, right? That's what N is 20 tries. So we try 20 times, comma. Our chance of success for each time is 1/4. So I'm going to put 0.25. So I put the chance of success for each trial. And then I want 6 successes. So again, make sure you don't flip these around when you enter the calculator. Your calculator goes N first, then P, then X. So what's your tries? 20 tries. What's your chance of success? 0.25, or again, 1/4 is a decimal. And then how many tries are you going to do? Well, I'm going to do 6 tries. You click enter, and you get 0.6186. Actually, 0.1686, my bad. 1686, or about 16%. And again, this is just calculated work, but you have to know that this is a PDF function for the binomial because you have an exact number of successes. So when you hear binomial and you hear x successes, think binomial PDF. And again, make sure you enter them in the right order here. If you don't, depending on how you entered it in, I'll show you here. If you entered it in incorrectly and you did 20, 6, 0.25, you get an error. And in this case, if you go to, it'll show you here that, well, you're going to look at it and say 6 can't be my x because this means that my chance of success is 600%, which is not true. You can't have 600% chance of success. So if you get an error, it probably means you swap the last two. So go back and swap 0.25 and 6's positions, and then it should work. So if you get an error, that's your clue that you probably entered the last 2 numbers in the wrong order. So number 22 says find the standard deviation of a binomial distribution with the values of n of 300 and a p of 0.68. This is just another formula. So the standard deviation of a binomial, sigma, is just root n p q. So in this case, it's root of 300 times 0.68 times, now remember Q is just 1 minus P. Q is your chance of failure. So P is your chance of success, which in this case is 68%. So my chance of failure is going to be 0.32 because it's just 1 minus 0.68. Make sure that root goes over everything. So number of tries total, chance of success, chance of failure, multiply them all together and then square root, and that's going to give us 8.08. That's our standard deviation. So once again, it's just another formula to memorize. It's a pretty small formula, but you have to remember that you will probably have to get your Q. Your Q might not be given to you. So if you don't see the Q, make sure you do 1 minus your chance of success, and that will get you your Q value. Okay? Again, chance of success, chance of failure. Think about them in that terms. It says the average unicorn deaths per year is 4.5. Use the Poisson distribution to find that there are 6 unicorn deaths in a year. So once again, this is a Poisson distribution, so we're going to use a p function, and this is exactly 6 deaths in a year. So to find the probability that there are 6 unicorn deaths. Not that there are at least or at most or no more than or no less than, but that there are exactly 6 unicorn deaths in a year. So this is another PDF function, okay? Because we want exactly X number of deaths. So we go to our calculator, second vars, we're going to go down to the Poisson one this time. So here's the Poisson PDF. We're going to click enter because it's the Poisson PDF. And the way you enter this is you enter your average first. So your average number of deaths is 4.5. So we're going to enter 4.5. Whoops, not 45, 4.5, comma. And then we're going to enter the number of deaths that we want to track, which in this case is 6. So average 4.5 deaths a year. We want, what's the chance that we get 6 deaths in 1 year? And it's about 0.1281, or about 12/13%, somewhere between there. So Poisson is a lot simpler than binomial because it doesn't have a lot to deal with. It's just, once again, average and number of successes, or in this case, number of deaths. Obviously, a unicorn death might not be a success in your eyes, or it might be, I don't know. But it's just the average, comma, and then what you're tracking. 6 deaths in a year, let's track that. And then they'll spit out the probability. So 24 says find the 5-number summary for the box plot below, or the set of numbers below. And once again, we could try to do this by hand, but why do that when we have a calculator? Again, it's going to save you a lot of time here. It's going to take a little bit of a time to enter the list, but that's fine. So we go second list. Whoops, actually, scratch that. We go just to stat, my bad, stat, and then go to edit because we want to edit our list. Let's clear out this list here. So you go up, clear, enter. And let's start entering our numbers. So 15, making sure we're careful here, 16. Now, these are in order, so some of you might actually find it easier to go by hand because they're already given to you in order. But I would still just use the calculator just in case they're nastier numbers on the final, so you can see how it's done in the calculator, so you can maybe save your time there. We have 3 20s, so 20, 20, 20, making sure I don't misclick a number here. 2 21s, so 21, 21. We have 2 22s, so 22, 22. 2 23s, so 23, 23. And then 4 24s, so 1, 2, 3. 3 24s, my bad, not 4. 2 25s. Okay. This is some sort of Zen moment, I guess you can have, entering numbers into a list if that's your kind of thing. 2 27s, 28, 29, and 29. And then 30, 31, 31, 33, 34, 35. It's like counting sheep, I know. Then we have 39, 42, and 48. So 39, 42, and 48. All right, so we got all our lists in. So now we're going to go back to stat. We're going to go over to calculate, one var stats, because we want one list, enter. And in this case, we have to go down a little bit because the 5-number summary is basically these numbers right here. Let me go one more. There we go. So these numbers right here, these last 5 numbers are your 5-number summary. Your minimum, your Q1, your Q2, which is just your median, your Q3, and your maximum. So we want to look for which box plot fits these numbers here. So 15 should be our minimum. Well, they all have 15 as a minimum, so that's not going to help me. 20 should be our Q1. So here's 20, 20, 20, 20. So they all have 20 as Q1, so that's not going to help us. So minimum is 15, Q1 is 20, minimum Q1, minimum Q1, minimum Q1. So they all have those. What about median is 24? Well, that one has it, that one has it, that one has it. This one doesn't. So median 24, median 24, median 24. This one is median 22. So that one's false. That one's not going to work. Then Q3 is 30. Well, here's 34, so that's not going to work. Here's 29, which is close, but not going to work. So then that has to be C. So you just go down the list and check to make sure which box plot has these in order. Starts with 15, then goes to 20, then 24, and then 30. And the last one, of course, is 48, and which they all had 48 on it. So once again, enter your list. It might take a while to do if there's a long list of numbers. That's fine. Enter your list. Find your box plot that best fits the list that you've given. And then another 24, because again, I can't count apparently. So a state holds a lottery that selects 8 numbers from 1 to 40, inclusive without replacement. Inclusive simply means that includes 1 and 40. So it's selecting 1 all the way up to 40, not between them, but including 1 and 40. To win, one must select the correct 5 numbers in the correct order. What's the probability of winning as a fraction? So the probability of winning is, again, the number of ways you can win divided by the number of ways total that can happen. Well, the number of ways you can win is just 1. There's only one way to get the correct 5 numbers in the correct order. If they just want the correct 5 numbers, then there'd be multiple ways of winning, because if we just need the correct 5 numbers in any order, you can get like 1, 2, 3, 4, 5, or 5, 4, 3, 2, 1, or 2, 3, 1, 4, 5. So there's a lot of different orders you can have there. But if I want the correct 5 in the correct order, that means there's only one way to do that. So if the numbers were 1, 2, 3, 4, 5, that's the only winning combination. You cannot have those numbers in any other order and still win. So that one was pretty easy to get, but how many things total, that's going to be more difficult because there's quite a few different ways these numbers can pop up. If I'm choosing 8 numbers from 1 to 40, there's quite a few different ways I can do that. Well, luckily we have a function called p. P allows me to pick, or as a function in your calculator that we've done in class 2, that allows you to figure out how many different ways you can arrange a certain number of items if you take only a little bit. So the way you'd say this is 40 P8. So you have 40 numbers and you're going to pick 8 of them. And you want to figure out how many different ways can that happen. So 40 pick 8, what's going to be 3.1008 times 10 to the 12th. By the way, you can do that in your calculator. You go to math, you go over to probability, and then right here is NPR. So what you would do is actually you would type in your 40 first. So you go 40, math, go over to calculate, NPR, and then you type in 8. And then you end up getting this number here. This little E12 just means times 10 to the 12th. So I write down this entire decimal all the way up to the 7, which I round to an 8, and then I just type in, or just write in times 10 to the 12th, just so I don't have to write out everything. So this would be how many different possible arrangements of numbers I can have. So 3.1008. So this is how many total possible arrangements there are. This is how many total possible arrangements are winning. So this is the probability to win as a fraction, which you could divide to get to a decimal if you really want to, but it says to leave it as a fraction, so we're going to leave it as a fraction. So a pretty small chance because this right here is quite a large number. It basically means take this decimal and move it to the right 12 times, and that's how large your number is, which is, again, quite large. So once again, one way to win, and then there's 40p8 ways to pick 8 numbers from 1 to 40. And again, the reason it's not C is because in this case, we need the correct order. So 1, 2, 3, 4 is not the same as 5, 4, 3, 2, 1. If it didn't need the correct order, then this would be a C here because we wouldn't care about the order. But we do care about the order, therefore P is the one that we go for. So we're picking the numbers, not making combinations. Number 25 says which cannot be a probability. Well, remember, a probability can be anything from 0 to 1. So 1 and 0 are okay. 2/5 is between 1 and 0, so that's okay. 0.45 is between 1 and 0, so that's okay. The only one of these that's not between 1 and 0 is 11/9. This comes out to be a decimal that's bigger than 1, so this is the one that cannot be a probability. This is over 100%, so that can't happen. So probabilities have to be either proper fractions, decimals less than 0 or 1, 1 or 0 themselves. And they have to be positive. So -5 could also not be a probability because you can't have negative probabilities. So you can't have them over 1, and you can't have them less than 0. So 26 here says, would tracking the time it takes for a medicine tablet to dissolve be continuous or discrete? Again, time is almost always continuous, so we're going to go with continuous. Because you have to measure time, you don't really count time. And again, time is something that takes place over an interval, so you can have like 0.567 of a minute. So time is almost always continuous in that case. So this one says use the density curve to answer the question. So this was when we kind of started doing normal distributions and we started to look at uniform ones first, and then we kind of worked our way up to normal. So this graph here is a probability graph. It represents the chance of these numbers happening and the probability of each being picked. So you're picking the numbers 1 through 8, and each number has a 12.5% chance, it looks like, to be picked. And we want the chance that we pick 1.6. So let's say we're picking a number along a stretch of numbers here. So anything from 0 to 8, each thing is a 0.125 chance of being picked. What's the chance that we get greater than 1.6? Well, 1.6 would be somewhere between 1 and 2, right? So we'll just mark it right there, about halfway, right? A little bit more. So that'd be 1.6. So if I want the probability of it being greater than 1.6, what I want is all this stuff in here, because all that stuff is greater than 1.6. I don't want this part because it's less than 1.6. I want the chance of my random variable being any one of these numbers here, from 2, 2.1, 3.7, 4, 4.85. Anything that's bigger than 1.6, I want the chance of it being that. Well, the way you do that is you figure out the area of this rectangle, because what we said here is that for density curves, area equals probability. That's how it's made, is that density curves are made so that area equals probability. So for this rectangle here, I want to find the length of the rectangle and the height of the rectangle, and then multiply them together to get the area. And like I said, the area would represent the probability. So this rectangle is 0.125 units high, so 0.125. And it's, well, we go from 1.6 to 8. So we'll do 8 minus 1.6, which is a total of 6.4. So it's 6.4 units long. Again, I just took 1.6 minus 8 to figure out the length of the rectangle I want. So my probability is simply the area, 6.4 times 0.125, which is going to give me 0.8, which is this one right here. So there's an 80% chance that this random number, whether I'm picking it from a hat or doing it on a computer or generating it from somewhere else, is going to be bigger than 1.6, a 0.8 chance or an 80% chance. So again, when you hear the word density curve, you're trying to figure out the area under the curve because that's going to represent your probability situation. Area equals probability for density curves. For 28, this is saying that when you have a set of data, some set of data, quartile 3 ends up being 450. What does it mean about 450 and how it relates to the rest of the data, or how the rest of the data relates to it? Well, Q3 is your 75% mark. because it's 3/4. So 75%, that's what Q means, is quartile, so 3/4. So this means that, let me put it in words here rather than trying to write it out because my handwriting's messy as it is. This means that 450 is the value that is greater than or equal to 75% of the data. So if these were, say, quiz scores or something, maybe you did a really big quiz worth hundreds and hundreds of points. This means that 450 is the amount of points you would have to get to be at or better than 75% of the other scores people have gotten. So 45% is the line, is the mark where it's more than 75% of the data and less than 25%. If saying this is a little bit difficult, you can always draw a picture to represent it as well. So for example, right here, you could have, here's a number, here's a number, here's a number. We'll just make a little list here. So think of this as your data. These are all the numbers that you have to work with in your survey or your analysis, whatever. 450 we'll say is somewhere in between here. So here's 450. And the way you'd show this is you'd say that 75% of your data is at or below 450. So this is 75%. And 25% of your data is at or above 450. So this will show me that you know that 450 is a spot where 75% of your numbers are below it and 25% of your numbers are above it. So if you want to write it out in words or draw it in a diagram, either way to get the point across is fine by me. So for 29, it says a student lost their note card for the final. They deduced that there's a 1 in 5 chance that it is in a random locker. What's the chance that if they go through all the lockers, they find it in the third locker they check? Well, let's make a list here. So we're checking 3 lockers total, right? 1, 2, 3. What's the chance that they find it in the third locker? So if it's in the third locker, that's a 1 in 5 chance of being in the third one, right? So there's a 1 in 5 chance that's in the third locker. But obviously, if it was in the other 2, we wouldn't need to go to the third. So we want the chance that it's not in the first locker. Well, if there's a 1 in 5 chance of being in a locker, that means there's a 4 in 5 chance of not being in the locker. So there's a 4 in 5 chance, whoops, let me try that again. 4 in 5 chance of not being in the first locker, a 4 in 5 chance of not being in the second locker. So what we're going to do is we're going to multiply these together, and we're going to end up with 0.128, or about a 12.8% chance of being in the third locker they check. So this is the chance that they missed the first time, they missed the second time, and they get it the third time. So 4/5 times 4/5 times 1/5. So you miss it, and you get it. And then that's the chance that that happens. So when you have this type of situation, list out your fraction, list out however many cases you have. So if this said 10th or 9th or 7th, I'd have 7 blanks, 10 blanks, 9 blanks, whatever blanks I need. And then each one look at what fraction would it be? Would it be a hit or would it be a miss? And normally the last one's going to be your hit and all the other ones before it are going to be your misses, because if you get it, you're obviously not going to check more lockers. There's no reason to check a 4th locker if I got it on my 3rd one. So all the ones before it are misses, and the last one is your hit. Moving along here. We have 5 student council positions. These are them. And we want to pick 5 from 20. How many different combinations are possible? So we have 20 people to choose from, and we're going to pick 5 student council positions. Now again, this is a case where order matters. So for example, if I have 5 positions, 1, 2, 3, 4, 5. Let's say we have homework advisor first, right? If I'm looking over my survey here, if I have 20 people to choose from, that means I can pick any one of 20 to be the homework advisor. So we'll put HA here for homework advisor. We'll put LI for lunch inspector. We'll put HG for hallway guider. We'll put LM for locker mechanic. And we'll put S for Steve here. So 20 people can be a homework advisor. Now, once I pick a homework advisor, I cannot pick that same person to be a lunch inspector. One person cannot have 2 jobs in this case. So there's only 19 people I can pick for a lunch inspector. And there's only 18 people I can pick for a hallway guider, because neither of these people can be a hallway guider. And there's only 17 people I can pick for a locker mechanic. And now there's only 16 people I can pick for a Steve. So it'd be multiplying all these together. So again, list out your spots and then figure out how many people you can put in each spot. And this is without replacement because once you pick a person for homework advisor, they can't be any of the other ones. So this would be another one where you'd go 20p5 in your calculator if you want to do this in your calculator, or because what this is basically just that. So your calculator does this operation when you type this in. It's just that this is easier to type in. Me personally, I would just do 20. Turn on here. I would just do 20 times 19 times 18 times 17 times 16 and get my answer that way. But again, if you want to do the P version of it here, you go math, go over to probability. Oh, actually, I keep forgetting. You have to type in your number first. So 20, because that's how many people you're choosing from, math, probability, NPR, and then 5. And then we get the same answer. So this is what the calculator does in the background. This is how you would type it in if you want to go down that route. Either way, we get 1,000, or actually not 1,000, but 1860, 480. So we have quite a few different possible combinations, over 1 million actually. But again, this is just the background version of what's happening. If you remember that 20 pick 5 is 20p5. Okay, P for pick. 20 people, pick 5 of them. How many different ways can that happen? 31 says over a 20-week period, a computer salesman sold 34 computers using a Poisson distribution, or Poisson. Find the probability that in a randomly selected week, the number of computers sold per week is at least 4 or 1. So over a 20-week period, they sold 34 computers. So we have to change that to an average first. So 20-week, 34 computers. So let's make that into an average first. 34 divided by 20 gives us an average of 1.7. So that's our mu. But again, mu is just how we represent the average, just the variable we use. You can use x bar as well as, I guess, but usually we use mu. So this is the number that we're going to use in our Poisson. Now, the first one here says, what's the chance that we sell exactly one computer in a week? So if we pick a week, what's the chance that one computer per that week is sold? Well, what we do is we go to our little calculator here. We go to second distribution because we're using a Poisson or Poisson distribution. So that's what that DISTR there stands for, is distribution. So second distribution. We go down here to where it says Poisson. And this is a PDF one because we have exactly one. We want, what's the chance that we get exactly one computer sold? So we do PDF, and then we type in our values. So we have an average of 1.7, so we're going to type in 1.7. And we want one success. We want one sell. And the chance of that happening is about 31%. So 0.31056. So 0.31056. Or again, about 31%. Now, part B here says at least 4. So this means you can have 4, or you can have 5, or you can have 6, or you can have 7, ... You can go all up. You just can't be less than 4, right? At least 4 means you just can't be less than 4. So what we're going to do for this one is we're going to do 1 minus the Poisson CDF. Remember, CDF, C stands for cumulative. So what CDF does is it adds up every possibility up to the value you enter in. So let me show you that. It makes a little bit more sense when I put some numbers to it. So if I go second distribution, I go all the way down to Poisson CDF, which is this one right here, the Cth option. It goes 9, 0, then ABC. So Poisson CDF, I click enter. I type in 1.7 because it's my average still. Then I type in the number that represents all the stuff I don't want. So if I want at least 4, that means I don't want 3, I don't want 2, I don't want 1, I don't want 0. So I don't want everything up to and including 3. So it's 1 less than what they're asking me. If I want at least 4, I'm going to type in a 3. Because what this will do is this will calculate the chance of it being anything from 0, 1, 2, or 3. This will calculate the probability of it being 0, 1, 2, or 3 and add them all together. So if I click that, that's going to give me that word decimal here. And then I'm going to take 1 minus that answer. and that's going to give me the low-ish probability of being 0.0931. So 0.0931, we'll just do 89 here just to make it nice and neat, which is about a 9% chance, so 9.3189%. So this is the CDF of 1.7 comma 3. So if you want at least 4, that means you want to figure out the entire chance of being 3 or less, and then take 1 from that. Because if you take 1 away from all the probabilities that are 3 or less, what you're left with is all the probabilities that are 4 or more. So imagine this as these are the ones we want, and then 3, 2, 1, 0. These are the ones we don't. That's why we're doing 1 minus all this stuff here. So we take away all that stuff. That's what this is here, that CDF function. We take away all the possibility of it being that, and we're just left with the possibility of it being more than 3. Because remember, 1 represents everything. So this represents everything that can possibly happen. Take away the chance of it being 3, 2, 1, or 0, and you're left with the chance of it being 4 or more. So when you have at least, think 1 minus the CDF, because it's different than just being exactly 1. Then 32 here, which probably isn't 32 because I messed up counting these twice, so it's 30 something, but probably not 32. But anyway, the average height of a Sasquatch is 108 with a standard deviation of 8. What's the chance that as a randomly selected or captured Sasquatch is less than 90? So this is a z-score problem, because if you want the probability that's less than 90, what you're going to do is you're going to figure out the z-score, and you're going to go to the value, 90, minus the average, 108, divided by 8. So this is the value you're checking, which is 90. This is the average that you have to deal with, which is 108. And this is the standard deviation you have to deal with, which is 8. So value minus average divided by deviation. We did a problem similar to this before in the same video. So if you want to go back and look at how we did that one too to get a refresher on where this is coming from, that's fine as well. But that ends up being negative 2.25. Now, this is the z-score. To get the probability, what you're going to do is look at that z-score table I gave you, or that's in the back of your book, to figure out what probability this appears to be. Unfortunately, I don't have one to show you here, but what it would look like is in the back of your book, I think it's table A-2, or in the z-score table I gave you at the start of the section, you're going to look for your probability of negative 2.25. So the way that would appear is on this column right here would be negative 2.2, and then on the top column will be 0.05. So you're going to look for where these two meet, and wherever they meet, that's your probability, which in this case ends up being 0.0122 if I looked at my table correctly, which I believe I did. So the chance of it being less than 90 inches high would be 0.0122, or about a 1% chance, which is pretty low. So you find your z-score by doing checking value minus average divided by deviation. You're going to get your z-score. Look it up in your table. The first two numbers are going to be on the left-hand column. The last number is going to be on the upper column. You find out where they meet, and then that's your probability. What's the probability that it's more than 110? Well, okay, this one's a little different now because it says more than. So here's the trick with the table. The table gives you less than values. So the table gives you less than values automatically. If you want more than values, you're going to start the same way, but you're going to take 1 minus what you get. So let me show you that here. So we're going to start the same way. Checking value minus average divided by deviation, which means that this is going to end up being 0.25. So in our table, we're going to look that up here. So this is actually 0.25 if you want to be clear about it. So you're going to look for 0.2 on the left-hand column, and then look for 0.05 on the upper column. Find out where they cross. And now we're going to cross at 0.5987. So this is the chance that it's less than 110. I want the chance that it's more than 110. So what I'm going to do is I'm going to take 1 minus 0.5987. So just remember, the table is less than, So if you want more than, you take 1 minus that value, which in this case would end up being 0.4013, which is about a 40% chance that's more than 110 inches tall. So again, might be something to write on a note card or something, but the table is always less than values. If you want more than values, you yourself have to go the extra mile and take 1 minus the less than value to get the chance of it being more than that value. So this is my final answer here. And then part C is the same type of problem, but backwards. So remember, our formula for z-score, like we did in the previous problem in the video, was your value minus your average, which we call mu. So again, this is just a symbol for average, divided by your deviation. And we want what is the value that separates the top 20 from the rest. So assuming the heights are normally distributed, which again, heights normally are, it looks like this. So we have that bell curve. And we want what z-score, what height rather, first we need to get the z-score, but what height would separate the top 20, so the top 20, from the bottom 80. So I want what number splits the entire, because remember, this bell curve, this represents the heights of all Sasquatches. So I want what number separates the top 20 tallest Sasquatches from the bottom 80 shortest Sasquatches. What number would do that? Well, I'm going to work backwards from my table. I'm going to look for what number will get me as close to 0.8 without going over here. What number would get me as close to 0.8 without going over? So in my table, I'm going to look in the middle and figure out where is the closest I can get to 0.8 without going over. And I think if you look in the middle, the closest you can get is 0.7995, because I think the next one is 0.8001. But you want to figure out what number gives you the closest you can without going over, and then you're going to figure out what is the z-score that goes with that. So you're going to look for the left and top numbers. So in this case, I believe the leftmost number ends up being 0.08, so 0.8. And the top number ends up being 0.04. And so my z-score is 0.84 because that's the number that goes with this value. So just to pause and recap here, because we're not done yet, but just to pause and recap. We figured top 20% means the bottom 80 is what I'm searching for, because remember, your table only does less than. So it doesn't do top 20. Your table won't give you the top 20. You have to think about, okay, if that means top 20, that means I'm looking for the bottom 80. Because again, everything's 100%. So top 20, take that away. I'm left with the bottom 80%, which is 0.8. Your table doesn't have 0.8 on it, but that's why you go searching for as close as you can without going over, kind of like the Price is Right. As close as you can without going over, which in this case, the closest you can get is 0.7995. And then from that value, you go backwards and figure out what z-score would get me there, which is 0.84. Then you have your z-score. You have your average and deviation from the top here. So here's your average and your deviation. And you're going to plug that all into our formula. So you're going to say 0.84 is equal to x, because I don't know my value that is separating there. I don't know this exact height value yet, but I know that the average is 108, forgot there for a minute, all over 8, because that's my deviation. Yeah, 8. Just want to check to make sure I was right there. So then you're going to solve this equation for x. So the way you start that is you multiply both sides by 8 to get rid of the divide by 8, and then you add 108, that's a 0 there by the way. You add 108 to both sides. So you solve it just like an algebra problem. And in this case, you end up getting 114.72. Okay? Again, if you don't know how I did that, I just times both sides by 8. Times both sides by 8. This goes away. I'm left with 0.84 times 8, which gets me 6.72 is equal to x minus 108. So you add 108 to both sides. Whoops. Let me try that again. Add 108, not 8. 108 to both sides. And that's going to end up getting you 114.72. So this is how tall you need to be if you're a Sasquatch. This is how tall you need to be in the top 20%. If you're anything shorter than this, then it means you're in the bottom 80. If you're bigger than this, that means you're above the top 20. But if you're exactly 114.72, that means you're in the top 20 and you're bigger than 80% of the other Sasquatches. So the last one's a little bit of a doozy. It always is when we first did it in class as well. Um, Again, you can come see me after class if you need extra help on this last one here because it is a little bit of a doozy and I didn't have any table to kind of work off of, so I had to kind of make my own, which made it a little bit more unclear, I know. But hopefully this helped you out here. Like I said, it's a lot of information I know, so take it piece by piece. Don't try to cram it in on one day because it's a lot to do on just one day. So take it bit by bit, do a little bit each day. That way your brain has time to sink and absorb that information. As always, if something still doesn't click, let me know so I can help you out further. Hope you enjoyed the video. Have a good day.